Hello family, this is our lesson 53. Before we get started on lesson 53, maybe let's take a moment to go through what we have covered so far in this unit, and then that will lead very nicely into what we're doing today for lesson 53. So let's take a look back really quick. What we started with was this idea that we want to know some kind of information about a population. Oftentimes, the information that we are most interested in, well, I guess I shouldn't say most interested. The most common information that we look at is the mean value of a population or the proportion of a population. It is very important that you understand there's a difference between the two. So mean applies to when you want to find the average of a population, which means it needs to be quantitative data. And then a proportion applies when we want to find the percent of a population that does something or is something. So that means you have to have categorical data. In our Can You Do 51, you had an example of quantitative data. So here you're interested in the average height. Here you're interested in the average number of steps. So we can add all those numbers and divide. And then in lesson 52, we start talking about categorical data. So in this one, we want to know, did you do your homework, all your homework last week? The categories are yes or no. In this one, we wanted to know the range of orders filled. So this would be quantitative. So now we're starting to mix them up. Problem 1 is categorical. Problem 2 is are numbers that can be averaged. So this would be an example of quantitative data. Number 3, we switch back to categorical data, and your categories are stars, crescent moon, rockets, astronauts, planets. So it is very important to know that there is a difference between finding the mean and finding the proportion. And often the data that you're looking at differs. So in one, you're looking at numbers. So not often. Always the data differs. If you're finding an average, you're looking at numbers. If you're finding a proportion, you're looking at categories. It is important not to forget, so I guess I should say it's important to remember, that we're not only interested in these parameters. We're not only interested in the average or the percent. We also may be interested in the range, and we saw that in the online orders problem. We might be interested in the median. We saw that in the Old Faithful geyser example in our notes. So most common, but also this is possible. So we start with wanting to know information about a population. The easiest way to get that is to take a sample, because often it's not realistic, possible, or doable to look at information from the entire population. Down here goes through the different ways we describe this information. So if it's coming from a population, we refer to it as a parameter. If it's coming from a sample, we refer to it as a statistic. So this column underneath the word parameter are your parameters, and this column underneath the word statistic are your statistics. Over here, unfortunately, we don't get fancy letters or symbols for these. We just have to write them out longhand. So page 1, we're talking about wanting to know information about a population, and to do that, we will take a sample. Then we go into, well, what would those samples look like? And what would it look like if we graphed all of the samples that were possible? So we did this for a mean, and then discovered that it really is quite a task to find all of the samples, because in many cases there are hundreds of thousands, millions, quadrillions of different possible samples. But what we ended up learning or seeing is that if you take enough samples, what your distribution will look like is a normal curve that is centered on the true value of whatever we're looking at. So if we're looking at a proportion, your sampling distribution will be centered on the true value of the proportion. If we're looking at an average, the center of your sampling distribution will be at the true value of the average. We actually saw that here. We saw that our true value, 75, was at the center of our sampling distribution. So we talk about getting information for a population when we have a sample. We talk about what exactly do those samples look like. We talk about, well, what does it look like if we plot all those samples on a graph? And then we talked about what is the shape of that sampling distribution. And I think that the best page for showing you the difference between the three things is this page. You have your population distribution, you have your individual sample distributions, and then you have your sampling distribution. And today, this is what we're focusing on. We're focusing on this sampling distribution. And it turns out that we can determine if the sampling distribution looks like this. So remember I said if we had enough samples, our distribution will look like this. We're going to talk about what exactly that means, that statement. Well, if we have enough samples. So also we have on this side, if we want the lowest variability, we want to make sure our design is good. We want to make sure our sample size is large enough. And if we want a estimate that is not biased, we want to make sure that we are sampling randomly. So today we pull all of this together. What is it going to take for our distribution to look like this? And this is low variability, this is not biased, and this is normally distributed. So how do we get this distribution? That's where we start today. We are starting with sample proportions because the requirements or the conditions for getting a normal distribution are different for the two parameters. So we have a whole page on sample proportions, and then coming up we will have a different page for sample means. So the graphic at the top is just the setup for your distribution. So this says I'm going to start with a population of size capital N and a given proportion of P. So the true population size, the true population proportion. Here's your population. We're going to take simple random samples. Remember, SRS stands for simple random samples of size little n. And we're going to calculate the proportion in each sample. Then we're going to plot it. So these two sentences are following this graphic. Here's your population. You take simple random samples of size n. You compute the proportion, and then you plot it on the or on a x-axis. What follows then is what you can see very little next to this curve. It turns out that our standard deviation can be calculated and that the mean of our distribution will be at the center. So how does that happen? Because it doesn't happen every single time. So how does that happen? Well, we have some conditions. So the shape is normally distributed if you satisfy what is called the large counts condition. The large counts condition. The large counts condition is verifying that if you take your sample size and multiply it by the true proportion, that's greater than or equal to 10. And if you take your sample size and multiply it by 1 minus the proportion, that is greater than or equal to 10. So if it is true that these two values are greater than or equal to 10, your distribution will be normally distributed, and you usually have to check it. Where does this come from? Well, to be frank, there is some heavy-duty mathematical reasoning behind what's happening there, and it's beyond the scope of this class. So if you were going to go into statistics as a major, you would eventually learn where the large counts condition comes from. But from us, we get a little, or for us, we get a little bit of a break, and we get to know the condition without having to suffer through the reasoning behind the condition. So if we check that this is true, and it is true, then our shape is normal. The mean of our sampling distribution would be equal to the true value of the proportion. So remember, this has some fancy subscripts. So what they're saying here is mu sub p hat. So the average sample proportion. We take all of our p hats, add them together, and divide by the number of samples. This is going to be equal to the true proportion. This is just fancy for this. That is a fancy way of saying this. Our distribution is centered on the true value. How do we get this? Because here we had to do some calculations. Here, the only thing that we're looking for is that you did random sampling. So here, all this requires is random sampling. If you take a random sample, your sampling distribution will not be biased. And then lastly, we can calculate the spread of our distribution, and that's right here. We can calculate the spread of our distribution with this formula if the 10% condition is met. So the 10% condition has to do with sample size. Remember, your spread has to do with sample size. And when we talked about variability, I told you guys that a bigger sample is always better. And now I need to clarify that statement. If you're being asked a question about how to reduce variability, a bigger sample size is always better. But now that we're getting into this portion of the unit, it must be said that a sample can be too big. So I'm going to say that again because it's really important to know. There is such a thing as a sample that is too big. So if they're asking about reducing variability, bigger sample size is always better. And in fact, in general, a bigger sample size is always better. But there is a case where your sample size is too big. So what would qualify as a sample size that is too big? If your sample is more than 10 times, well, no, I have to say that a different way. Let me show you the formula. Your sample has to be less than or equal to 1/10 of your population size. So your sample cannot be bigger than 10% of the population. Your sample cannot be bigger than 10% of the population. This is like the accepted form, but I like to think about it as looking to see if you multiplied your sample by 10, is that less than or equal to what we think the population would look like, or how many people would be in the population? And I'm going to clarify this a little bit with numbers in just a second. You have to check this condition, so I'm going to try to be as clear as I can on it. So the general way of writing it, or the generally accepted way of writing it, is your sample cannot be bigger than 10% of your population. Sometimes it's easier to take your sample size and ask yourself, is my population bigger than 10 times my sample? So over here, I'm going to write some notes next to this standard deviation to clarify this. So if your n is equal to, let's say, 5,000. Let's look at two sample sizes. Let's look at 50 and let's look at 600. Okay, so is 50, and maybe I'll write this on a Post-it note. Is 50 less than or equal to 1/10 of the population? Well, is 50 less than or equal to 1/10 of 5,000 is 500. So this sample size is okay. Now you may want to think about it like this instead. Is 10 times 50 less than or equal to the size of my population? This is the one that I prefer because it makes more sense to me. So I would ask myself, is 500 less than or equal to my population size? And in either case, the answer is yes. And we'll see many examples of this. So here, this sample size is okay. Now, let's check 600. So either way, we could say, is 600 less than or equal to 1/10 of 5,000? Well, 600, is that less than or equal to 500? No. Not okay. The other way is 10 times our sample size of 600, is that less than or equal to our population? Well, that gives me 6,000. Is that less than or equal to 5,000? No. So this sample size is too big. So there is a restriction on how big your sample can be, and that restriction is you cannot have a sample size that is more than 10% of the population. There's two ways to look at that, and I've listed both here. We're going to leave this box off for now. We're going to skip this box until we feel like we have a good handle on what's happening. I'm going to zoom out now and hopefully recap so that we can actually try a problem. So when you take a bunch of samples from a population and graph them, you can get a sampling distribution. That sampling distribution will be normally distributed with a center at the true value of the proportion and a standard deviation that can be calculated. In order for those three things to happen, normally distributed, center at the true value, standard deviation can be calculated, there are conditions that must be met. And that's what you see in these three boxes down at the bottom. This is the most important part of this entire page. This is a summary of all the things you see up here. So they're saying a sample comes from a normal distribution that is centered at the true value and has a standard deviation that can be calculated. It is normal if you satisfy large counts. Now remember, that's your n times p greater than or equal to 10, n times 1 minus p greater than or equal to 10. It is centered on the true value if you took a random sample. And you can calculate the standard deviation if you satisfied the 10% condition, or you've checked 10 times n is less than or equal to the population size, or the sample is 1/10 of the population size. Why is this important? Why is this important? That's what we see on our next page. So this problem is an example of why we're interested in the shape of the sampling distribution. Because it turns out we can make some pretty cool calculations or estimates because our sampling distribution is normally distributed. So, do you drink the cereal milk? A USA Today poll asked a random sample of 1,012 U.S. adults what they do with the milk in the bowl after they have eaten cereal. So I'm going to grab a highlighter and I'm going to start highlighting things. So a random sample of 1,012 U.S. adults. Let p hat be the proportion of people in the sample who drink the cereal milk. A spokesperson for the dairy industry claims that 70% of all U.S. adults drink the cereal milk. Now, the last part is very important, and it says, suppose the claim is true. Suppose this claim is true. So we are given our sample size, we are given our proportion, and told that it is a true proportion. First question, what is the mean of the sampling distribution and why? Well, the mean of our sampling distribution, so the mean of our samples, this means the mean of our samples, is going to equal the true proportion value. And the prompt tells us that that true proportion is 70%. Why? Because a random sample was taken. How do I know it was a random sample? Because it says a USA Today poll asked a random sample. So this letter A is this portion of this statement you have here. This is your mean if it's a random sample. Okay, next up. Find the standard deviation of the sampling distribution of p hat and check to see if the 10% condition is met. Okay, so sigma of p hat. And in this case, I'm going to write the formula for you, but when you do these on your own, you don't have to write this formula down. So the formula is p times 1 minus p divided by the sample size. That's all under a big root. Where am I getting that from? Right here. Okay, so let's plug in those values. Big root, p is 0.70. 1 minus p is 0.30. Divided by our sample size of 1,012. When I put this into my calculator, I like to enter it as a fraction. So I like to enter it exactly like you see it here. So how we do that is we hit the blue button and the x squared button. That's going to give you the root. But then to hit the fraction, you hit the green button and the y equals button. You select the first option, and that's going to give you your fraction. So I'll type in 0.7d times 0.30 all over 1,012. And that gives me a standard deviation of 0.0144. Remember, there is no rounding convention. So you basically just round to whatever you feel the most comfortable with. I usually on standard deviation go 3 or 4. Maybe I'll make a note to myself that to get the fraction, I have to hit green button, which is alpha, then the y equals button at the top. And then it's option 1. Hola. You need a key? Uno momento. No, I got it. I was talking to my kids that I was recording to. Okay. So now we have to check to see if the 10% condition is met. And remember how I told you that I like to check 10 times n? So I'm going to say 10 times n equals 10 times 1,012. That equals 10,120. And now we ask ourselves, do we think that there are more than 10,000 U.S. adults? Because our population is all U.S. adults, because that's who we sampled. So do we think there are more than 10,000 adults in the United States? Definitely. There are probably 10,000 adults in Magna. So we're going to say because n is less than or equal to 1/10 of n. And then in parentheses, I'm going to say there are more than 10,120 U.S. adults. In fact, it may be better to say here, because 1012 is less than or equal to 1/10 n. Pause. Okay, I'm back. Cute Mia came in to get something. So I have to wear my mask. But back to business. Okay, so we just checked our 10% condition. And I checked it by asking myself, is 10 times my sample less than how many things are in my population? So I said yes, or I said I can calculate this because I know that 1,012 is less than 1/10 of all U.S. adults. Well, how do I know that? Well, because I did this calculation, or I verified this in my head. There are definitely more than 10,000 U.S. adults. This portion here, you don't necessarily have to include that. What I have in the darker writing is all you would need to write. I just wrote this out for you guys so that you could see exactly where I was getting that from. So we have checked our center of our distribution is at the true proportion. We have calculated our standard deviation, and we have checked the conditions that make it so that we know that those things are true. Then the last step is asking the last condition is asking, is the sampling distribution of p hat approximately normal? Check the large counts condition. So large counts says that n times p has to be greater than or equal to 10. So let's check that. N is 1012. True p is 0.70. If we multiply that together, we get 708.4. So that one is satisfied. 708 is greater than or equal to 10. The other thing we check is that n times 1 minus p is greater than or equal to 10. So we do 1012 multiplied by 0.30 this time. And that gives us 303.6. So that is satisfied. So we can say the sampling distribution of p hat is approximately normal. And you could flip these. You could say the sampling distribution of p hat is approximately normal because, and then write this out. So we have just verified every single thing about our normal curve. Okay, well, I told you that this is why this is important. This problem shows why this is important, or why this is a pretty cool thing about sampling distributions, but all we've done is check conditions. So it's actually the last portion that shows you how important or helpful this property of a sampling distribution can be. So this problem says, of the poll respondents, 67% said that they drink the cereal milk. So that's what we get from our sample. Remember, we took a sample of 1,012 U.S. adults. We calculated how many of them drink their cereal milk. 67% of them said they drink the cereal milk. Well, now they're saying find the probability of obtaining that sample value if the milk industry's claim is true. And then it says, does this poll give convincing evidence against the claim? So we're finding a probability and then using that probability to test a claim. Okay, well, we now know that our sample comes from a normally distributed, and I'm going to write it out as norm, population with a mean of 0.70 and a standard deviation of 0.0144. They are asking us to find the probability, capital P, that we would get a sample value 67% or fewer. So they're specifically telling us that they want us to find p hat less than or equal to 0.67. So they're asking us, what is the probability you would get a sample that low or lower? Well, now that we know this is normally distributed, we get to use our normal curve. So I need to find my purple z-table. This is why the property of a sample coming from a normal distribution is so cool or important, because now I can use the normal distribution to find this probability. So you calculate z just as we have done before. So I'm going to write it underneath my z. We take our sample value, subtract the true value, and divide it by our standard deviation. So if you have a Post-it note handy, I would grab one so that you can keep this handy. What we know z to be is mu subtract, just kidding, x subtract mu all over standard deviation. Well, what this is in our case is p hat subtract our true value of p divided by the sigma of p hat. Okay. So I'm going to put that on my paper. So that's what I did here. P hat minus true p divided by standard deviation. Okay, this is less than or equal to, and now I got to plug that in. Now that I know how to get a fraction in, I'm just going to use that once again. So 0.67 subtract 0.70 divided by 0.0144. I get negative 208. Well, that's equal to, I go to my z-table, I'm on the negative side, I go to negative 2.0 and over to 8, that's 0.0188. If you want to know what percent that is, multiply by 100, thank you, and that would give you 1.88%. Okay, way back at the beginning of the year, we talked about testing a claim. And the examples that we talked about were, do we think that this lady in the UK can smell Parkinson's disease? Do we think that there was hiring discrimination when some pilots were chosen for management positions? And then do we think that a guy selling his Ford Focus, he claims that his Ford Focus gets like 42 miles per gallon, do we believe that claim? And every time we tested that claim, we looked at a dot plot and we said, well, how many times did this happen in our dot plot? And there was a cutoff for what would be convincing evidence, and that cutoff was 5%. So if the probability that we would get a sample this low is 5% or less, it is convincing evidence. If the probability is more than 5%, then it's fine. It in some cases is not likely, but it's possible. So in this case, we have convincing evidence. This is too low. They're saying the probability that you would get a sample value this low if p hat is truly 0.70 is only about 2%. So it's possible that this is true, but this is convincing evidence that it's probably not true. So here's how we write that, and then this is the last thing for this part of our lesson. So just writing this out. We're going to say yes. This poll gives convincing evidence against the claim. And the claim is p hat equals 0.70. It is not plausible to get a p hat less than or equal to 0.64 if p is 0.70. Why is it not plausible? Because the probability of that happening is 2%. That's too low. So this is convincing evidence against the claim. Okay, so at this point, try the questions. Try the questions below, and in the next part of our lesson, it'll go a little bit quicker. It's page 509, and we're just going to practice 2 more problems like this, and I'll show you the amount of work you're supposed to show to complete one of these problems. Okay, love you guys.